Good afternoon, Professor.
Good afternoon, Caroline. Good afternoon. Awesome. Awesome. Good afternoon, Kevin. Good afternoon, Caitlin. I'm watching this time. Okay. Hold on. Good afternoon. Good afternoon, Stephen. Oh, I missed two. Wait, okay. Caroline definitely gets the prize. But wait, okay, sorry. No, yes, good afternoon, Caroline. Good afternoon, Kevin. Good afternoon, Caitlin. Good afternoon, Amanda. Good afternoon, Amy. Good afternoon, Stephen. Good afternoon, Euben. Okay. And good afternoon, my board, which is coming back, we think. Wait. Okay. Oh, good afternoon, Sean. Okay. Hey. Good afternoon, Adon. Okay. Okay. And good afternoon, Mackenzie. All right. So again, just to repeat and not dwell, the exams are just coming back way more slowly than they should, but they're just coming back in dribbles one at a time. If you have gotten one, that's terrific. And if you have any issues, you can talk about it with me at any time, or you can make an appointment. If you haven't gotten one back yet, that it reflects nothing about you as a person. It probably reflects more about the first letter of your first name, actually, than anything else. And you will get it. And then no matter what time it is or when you get back or what, there will be time for you to discuss with me if you're worried about anything. It is probably the case that I'm less worried than you are. Anyway, they're just coming. I continue to apologize. I continue to do them. And all the dust will settle by the end of the semester, with the benefit of the doubt going to everybody. So let's get back to the material. And if there's any questions or anything, put it in the chat, please. Okay, we're going to get back to the material now. This is actually material that I find very exciting and very important. We're all about electrostatic field lines. Yes, we're all about electrostatic field in general right now. Last time we had looked at a bunch of different pictures of electrostatic field line diagrams. Again, today we'll go back on the web and look at various pictures just to get an increasing sense of how to read them and what they mean. And of course, these are all pictures, but they are quantitative representations. So I'm dwelling on field line diagrams for a little while in this class, like for a few classes, because they're not just rough sketches. Field line diagrams are like vectors or graphs in the sense that they are very specific, very precise representations of something quantitative that's going on in reality. And like graphs or like vectors, if the field line diagrams are written or drawn carefully enough and precisely enough, then they actually do computational work for us. Last way to put this is field line diagrams are also like free body diagrams from Physics 203. All these kinds of very specific, very precise, very accepted diagramming techniques that we have in physics and in science, or like molecular models and things like that you do, in organic chemistry and stuff. I hope it's clear to everybody that these diagrams that we draw, they are not just rough sketches of a sense or an impression of a situation that we have in our head. I mean, we do that a lot in science. We certainly frequently begin a problem with a rough sketch of our sense of the situation, and that's very, very important. but there's a difference between a sketch and a diagram. And many types of diagrams that we do, including graphs, including vector addition diagrams, Pythagorean triangles and so forth, including free body diagrams, many diagrams that we do in science are much stricter than just rough sketches. And what I want to emphasize, and you're going to see today, is that with many diagrams, you're not drawing what you think you already know or understand about a situation. You're drawing the diagram according to very strict rules, or you're programming a computer to draw a diagram according to very strict rules, such that when the diagram is finished and the diagram is complete, then the diagram reveals things going on in the situation, reveals quantities and measurements and relations that are then used in a quantitative way. In other words, we don't know what's going on and then draw it. Often we draw things to find out what's going on, right? And that works, that can work. Diagram, and remember, a lot of these things, such as vector addition diagrams and free body diagrams, a lot of these things existed before electronic calculators, to say nothing of computers. So you please remember that strict diagrams in physics and chemistry and so forth, strict diagram techniques are calculators unto themselves. They're like what we did when we didn't have calculators, and what we continue to do to this day, because there are still things that diagrams and so forth do that that a calculator does not. Okay, so we take them very seriously, and when we talk about diagrams, just like when we talk about vectors or we talk about graphs, we talk about them a lot, not just because we want to be talking about some random picture that's on the page, but because by talking strictly about the picture, as long as we know the rules that were used to draw the picture, and as long as we believe that the rules were followed strictly, then when we talk about a picture, we really are ultimately talking about reality. Actually, the most specific version of everything I'm saying here, I can't even believe I didn't think of this before. It's much like maps, right? Like maps of that are now in GPS or now in the computer, but maps of the world. You take out a map to figure out what's going on, and you say, oh, you got to go 20 inches north on the map. You're saying something really, you're saying, oh, we've got to go 20 miles north in reality. You know what I'm saying? Okay, I'm getting carried away. But the point is, we trust maps to bear a one-to-one correspondence to physical reality. We trust them so deeply that we can end up talking about the map and using map language, and we all understand that that is shorthand for talking about reality. Okay, so same thing about field line diagrams. That's where I'm going with this. That I'm going to continue talking about field line diagrams today, and it's because by talking about field line diagrams, what we're really actually doing is talking about how fields occupy space. Okay, so I'm going to change the view on the screen. I'm going to be flipping back and forth between the board, the whiteboard today, and those Google images again. What we're going to be doing right now on the whiteboard, and I'm going to change it view on the screen. I'm going to give you 7 simple rules for how to win friends and influence people. No, I'm going to give you 7 rules for how to draw any field line diagram. Now, if I had my way, we'd have 7 more months of this class, and we do a lot of practice, spending a lot of days drawing various field line diagrams and getting really used to drawing them. Okay, we don't have that. You'll draw a couple. You might draw one on the final exam, blah, blah, I don't know. You'll draw a couple. We don't have time to draw a lot of them, and I know that. But we'll draw some. But the reason I'm going to spend so much time, good afternoon, thank you, good afternoon. The reason I'm going to spend so much time today telling you how to draw them and then showing you the drawings, okay, is not because I'm expecting you to become expert in doing that or something, but because I'm trying to reinforce to you that these diagrams, in fact, I'm going to switch. Well, I'll switch screens in a second. I want to emphasize to you that the more complicated a situation, the more complicated and intricate the field line diagram will look. And the more complicated a field line diagram looks, maybe the more it looks like, oh, well, I could never. I mean, maybe if I'm lucky, I could read this, but I certainly could never create one. But I want to show you by the end of today that no, like actually anybody can create a field line diagram. A computer will do a more precise, maybe more beautiful job of it, maybe. But anybody can create one. It's simpler than it looks to do. And again, when you look at a certain electric situation, like a proton over here and an electron over here, I want to know what the field looks like, or or 2 protons over here and 7 electrons over here. I want to know what that field looks like. We don't say to ourselves, oh, I better. The reason we want to know the field is to know the magnitude and the direction of the force waiting to happen at any point in space due to the 5 protons over here and the 7 electrons over here or whatever, right? So the field line picture shows magnitude and direction of the force waiting to happen at the force per charge at every point in space due to some collection of points of charge, right? But the thing I'm going to say one more time, at risk of repetition, the thing I'm going to say one more time before diving into these rules is that what we don't do is say to ourselves, well, gosh, I don't know what the magnitude and the direction is of every force waiting to happen in every point in space. So I don't know what the magnitudes and directions are. So how the heck am I supposed to know how to draw the field line picture? No, what we say to ourselves is, I'm going to sit down and follow the rules of drawing a field line picture. And if I just blindly follow the rules and follow them carefully, the picture will create itself. And then I'll be able to stand back and look at that picture and say, oh, that's how the force per charge is acting at every point in space due to this collection of source charges. Okay, so that's the idea, is that by me telling you the rules of designing the field line picture, you can hopefully have a better sense of really what we believe about the shape and character of electrostatic fields in space, in reality. Okay, so here I go, but there is something in the chat. Hold on one second. I'm sorry, let me just look in the chat and then I'm going to go. Oh, good afternoon. Oh, I thought there was. Oh, good afternoon. Oh, and I'm sorry, I never said good afternoon to Samaya. I'm sorry, I see you, Samaya, and Mackenzie. Mackenzie. Good afternoon, all of you. Okay, and good afternoon, direct chat person. Okay. So here is the first rule. Here's the first rule for creating an E-field line diagram. First, you choose, and that says choose and maintain a scaling factor. For example, you could choose, for example, 8 field lines per or for each coulomb of source charge. So that would be an example of a rule. Any rule really is the number of field lines that you're going to draw per each coulomb of source charge. Okay, and then you're going to obey this scaling factor consistently and symmetrically. Okay. So let me show you. So I'm going to switch screens right now. So did you write that? Stop me if you didn't write that down. But the first rule is you choose a scaling factor, such as 8 field lines per coulomb. And 8 is a realistic example. I'm going to show you in a second. If you're doing things by hand, 8 is a very realistic example. As if you're rendering things by computer, your scaling factor might get much more precise, or it might be a much higher number than 8. Right, but let me just show you a quick example of what I mean by this. Wait, that wasn't. Sorry, let me do that. Oh, that's so weird. Why did it just wait? Oh, okay, but sorry, it's weird that it's. Okay, yes, I want to start with, if we start. Okay, start with the picture on the left. right? So that's the field line diagram. That's the field. There's the simplest field possible. The one on the left. The one on the left is the simplest field possible. It's where this whole discussion begins. It's the field due to a point charge. Okay, a positive point source of charge. Remember again, please, that the charge creating field is called the source. So even if we have more than one point of charge creating field, we would call each of them the source. Anything that's creating field is called the source. Again, for example, in the picture to the right, picture B, there's two sources. One is positive, one is negative, but we call them both the source because they're both objects in the universe that are creating field. Anything that would experience this field would be called a test charge. Okay, so again, going back to the left picture, we have a source, we have a point source of charge. Let's assume for the moment that it's 1 coulomb of charge. Okay, then that means the person who drew this picture picked literally a scaling factor of 8. Like what they said to themselves is, okay, I got 1 coulomb of charge. It's creating field everywhere. Like lines are going everywhere in space. That is the idea. Any point in space you pick, we believe that there is a field line there pushing test charges in some direction with some strength. But we're not going to draw an infinite number of lines. We're going to draw a representative, like cross-section of lines. So the person or the computer that made this picture decided, okay, for each 1 coulomb of charge, I'm going to draw 8 lines coming out of the 1 coulomb. And so they drew 8 lines, and they picked 8 for a reason, because you can have a cross, and an X, right? And then they deliberately, and this is part of the rule, they made those lines come out symmetrically, right? If they had chosen 4, they would have made 4 come out symmetrically. And the reason they didn't choose 6 is because it's sort of hard. I mean, they could have chosen 6, but it's sort of hard to make 6 come out symmetrically, right? So they chose a scaling factor of 8. Now, 8 lines are coming out of that charge. So in the picture to the right, you see, if we're consistent, then when we go to the picture to the right, or let's imagine this is all one big picture. Let's imagine that this is the field. Well, can we do that? We can't really do that, but go to the right and say the right now is now like a dipole. It's some amount of positive charge over here to the left and some amount of negative charge over here to the right. Well, if they're following their scaling factor consistently, right, then it seems to me that the positive charge in picture B must not just be like 1 coulomb of charge. Presumably I think it's like 2 coulombs of charge. I mean, I'm looking quickly, but I believe there's 16 lines symmetrically coming out of that left-hand positive charge, right? So we're gonna. That's the idea. Is that from here on in, when you're drawing a picture or a set of pictures, once you have a scaling factor, you use that scaling factor consistently and symmetrically. They had assuming they had twice as much positive charge, creating field in the B picture, they made twice as many arrows come out of it when they started their picture. Okay. Okay, so that's rule number 1. I'm going to go back. Stop me if you don't. So you choose a scaling factor. Now I'm going to go back to, how do I do this? Back to the other thing. Calling Gus Johnson. Okay, so that's rule number 1. Now, rule number 2. Okay, rule number 2. So you pick your scaling factor, then you start drawing lines. Okay, how do you draw the lines? Like where do you? Well, every field line will start at a positive, or put another way, any positive you see, you start making field lines come out of that positive, and you make them come out symmetrically, like we just said. If there aren't, so every field line that you ever draw must start at a positive, or it can come in from infinity. I'll get back to that in a second. But every field, but that's the only 2 options for the beginnings of field lines. They either start at a positive or they come in from infinity. Similarly, every field line must either end at a negative or go to infinity, in effect, not end at all. Okay, so another way to put what I'm writing here is, if field line is going to start anywhere, it has to start at a positive. And if a field line is going to end at all, it has to end at a negative. Now, like, what do I mean by infinity? For one thing, well, on a piece of paper, I mean the edge of the page in a way. But what am I saying with this? Like, again, honestly, I can never resist mentioning that when I remember hearing this as a sophomore in college in 1990. And it made no sense to me. I mean, I remember where I was sitting when I heard this, and it made no sense. First of all, I was like, what do you mean end at infinity or go to infinity? I'm like, I understand infinity sort of, but like, aren't we talking about drawing here? Like, where's infinity is in my drawing? Like what? And second of all, more to the point, I was like, wait, all right, so you're saying every positive, you're saying every field line either starts at a positive or it doesn't start at all. And every line must end in a negative or it doesn't end at all. And I was like, well, I sort of got that. I was like, as opposed to what? Like, what other options is there? What are you even saying? What do you mean that, okay, so they start at positive and they end in negative. Like, what's your point? What their point is, what this point is that what field lines don't do ever is start or stop spontaneously in the middle of the page. This is a huge point, far huger than I understood when I learned it the first time. What we're saying is that these lines are not vectors. They don't have tails that are just sitting there in the middle of the page, and they don't have tips that are just sitting there in the middle of the page. They don't start or stop spontaneously. If they start at all, they start at a positive. If they end at all, they end at a negative. Otherwise, they come and go forever. Now, what forever? What? So let me go back to the picture now and show you what I'm saying with this. Go back to the other picture. Yeah, okay, so here, right. So back to this picture now. Notice, so what I'm really saying first and foremost about field lines is they are built and constructed from vectors. They are meant to convey the same information that vectors are meant to convey, but they are not vectors. They are not finite little arrows with particular meaningful lengths. Look at the picture on the right, for example. Sorry, hold on. Okay, look at the picture on the right. It was drawn by following these rules. Like, so a person, they picked a scaling factor. They went over to the positive. They started drawing lines coming out of that positive, right? Every line that they could, they connected over to the negative. Every line that they could, they connected over to the negative. If the positive and negative were equal in opposite charge, then every single line would have gotten, if they're equal in opposite charge, then that means 16 lines have to come out of the positive, 16 lines have to come into the negative, then each one of those lines will be accounted for. Each one of those lines will start at the positive and end at the negative. End of discussion. And notice, like that's an if, okay? Notice that all the lines that very obviously do that, any line that very clearly starts at the positive and goes to the negative, has arrows along the way on the line. Like it has arrows in the middle of the line, unlike a vector. A vector always has an arrow as a tip at the end of the vector and as a tail at the other end. But see, these lines don't have ends. So the arrowheads are just like placed intermittently along the line. The arrow is indicating direction, but the fact that it's just sitting there in the middle of the line is very strongly trying to convey to you this line doesn't end at the arrow. It keeps going until it hits a negative. Okay, that's number one. Number two, there are some arrows like that where you can't see them joining up. Like into the left of the B picture that's on your screen right now. To the left, you see almost pointing straight up from the positive, you see a line that's going up and it just seems to fade out, at the top of the page. It doesn't seem to connect up to anything, but you notice that the arrows are still in the middle of it, like I was saying a minute ago, and it just like fades in the middle of the page. And then there's this other arrow, on the other side there's this other line, pointing down to the negative on the other side, and it has arrows along the way in the middle. So what they're telling you is, as you can imagine, as I'm sure you've guessed, they're saying, look, we just ran out of space on the page. But you can tell by that line, because the arrows are in the middle of it, because the arrows don't terminate the line, you could tell that the idea is that this one's going up and then up until it gets to a point in the page that we can't see. And then it bends over. It follows the pattern, in other words, of the lines that we can see. It bends up and it hooks in to the negative on the other side, right? Like there's a very clear pattern that's being indicated by the lines that you can see. So any lines that get cut off, they're specifically telling you to believe that those lines still follow the same pattern. You can tell because the arrows are intermittent along the way of the lines. I hope I'm making that clear. As opposed to, okay, so all of those lines are following the rule that says, each one of those lines is starting at a positive and it's ending at a negative. No line is doing anything else but that. If you were to go down, if I were to scroll down and start looking at like more complicated pictures, say the one all the way to the left, picture A here in the middle of your screen, same idea is happening, right? You got a bunch of lines, or even better. Well, yeah. Pardon me for a second. I just want to think about this for a second. Yeah, okay. Right. Look at picture A. In between the positive and negative, you have a bunch of lines that are doing what I just said a second ago. Like they're clearly going from positive to negative, and you can tell that they're terminating at the negative because the arrowheads are placed like right in the middle of the line, as I indicated before. But then you've got some lines flying out from the positive to the left of the positive. You've got some lines, some field lines flying out from the blue positive point source. And those lines that are coming out, they do have tips at the end of them, right? They do have tips at the end of them. That's a big distinction. The tips are not intermittent. The tips look like vector tips at the end of those lines. So first of all, apparently those lines are not hooking up and following the pattern of the others and joining over the negative on the other side. They're not doing that. Those arrows almost look like they are vectors. I mean, they have a tail at the positive, and then they have this tip at the end of the line. They almost look like they're vectors. But again, I have to stress to you, they're not vectors. The first way I know that they're not vectors is those are curving. Vectors don't curve. And they all, so that's number one. Number two, are those things actually ending at the arrowhead? No, they're not. The fact that if you look at the rule that I just stated, and here's the importance of the rule, the fact that those arrowheads are at the end of those lines, all the way to the left of the positive charge in picture A, the fact that those arrowheads are at the edges of each of the lines is indicating that those lines go on to infinity. It means, look, we just ran out of room on the page, but these things just go on forever. So it's a subtle distinction, but just like the lines in the first picture I showed you, they're saying we ran out of room on the page, but follow the pattern. You can see that these lines will go off the page and then they'll come back and they'll hit the other one. And you can tell that they're going to come back because they have arrowheads in the middle of the line. Here, they put the arrowhead in the end of the line. So they're saying, hey, we ran out of room on the page, but we're telling you what the pattern of these lines is. They're going to just go on forever. They're never going to come back. And that means the field is just going to go on forever there. Now, those lines are spreading out from one another. They're curving away from one another. So they would get farther and farther away from one another as we get farther and farther from the page. So as you'll see in the next rule, the field is presumably getting weaker and weaker as we get farther and farther to the left. But what I'm saying, bottom line is, every single field line is either going to hit a negative or go off to infinity. And every single field line is either going to start at a positive or come in from infinity. Those are the only two options. Bottom line, field lines do not spontaneously start or stop in space. If they start or stop, it's at a positive or negative charge, respectively, right? Therefore, field lines do not have meaningful length. Vectors have length. Field lines don't. They just have whatever length they need to have to complete the page or to go from positive to negative. Okay, I said a lot about that, but is there one more thing I want to say? Yeah, I'm going to go back to, there's something in the chat. I'm sorry, there's something in the chat. Oh my God. That's a great question. Wait, great question in the chat. And I really hope you ask a lot of questions today, any of you. I mean, I'm psyched for questions, and there also were many in the other class. So someone is saying in the chat, in the private chat, in the direct chat, someone is saying, can the lines of one charge be curved on the left side? And what that person's asking, and I'm gonna give a short answer to that right now, and then I'm gonna say more about it in two more rules. I believe that person's asking, like, look at this one charge here in picture A, all the lines are straight. But then if you look like in picture B, and particularly the lines on the left of the positive charge in picture A here, the lines are all straight. But then you look to the left side of the point charge in picture B, like it's a point charge, right? I mean, it seems like we shouldn't get the same picture. But because that point charge is near another point charge, a negative one, the lines on the left of it seem to be sort of curving. And it's a really good observation. If I'm understanding this question right, it's a really good observation. They're basically noticing, wait a second, when charges are like near each other, it seems like the lines are allowed to curve. But when charges are by themselves, do the lines not curve? And the answer is correct. If a charge is by itself, if it's a single point charge, like in A, the lines will not curve. They will be perfectly symmetric, like seen there. They start to curve when you have more than one charge going on, and only when you have more than one charge going on. I'm going to say more about that in the next couple of rules, but you are absolutely right to notice that the lines seem straight when the thing is by itself. That is not a coincidence. They must be. And they start seeming more curved when the charge is not by itself. The overall, that's a great observation, actually. And I say, I'm going to say more about it, but the overarching theme that you're noticing is that a field line picture has to be as symmetric as it possibly can be. A field line picture has to be as simple, has to be only as complicated, only as asymmetric as the arrangement of charges. Excuse me. A field line picture will only be as complicated or as asymmetric as the arrangement of source charges that's creating the field. So the field lines are always symmetric as they possibly can be. If you just have one point source causing field, then you can draw the lines coming out of it perfectly symmetrically, perfectly straight, like one up, one down, one left, one right, one northeast, one northwest, etc. Right? The lines only started curving once we had another charge near, because curving the lines was the only way we could keep the lines as symmetric as we could, while still having lines leave positive and enter negative. Like what I'm trying to say, I'm going to say more about this, but what I'm trying to say is the lines always have to be as simple as they can be while still following all the rules. Now, I've only given you 3 rules so far, so I have to give you more. I have to give you the remaining rules to really see this. But the lines are always as simple, the arrangement, the pattern of lines is always as simple as it can be, given all the rules, which is why anybody really can draw them, even though they look very intricate. Okay, I'm going to go on, but it's a great question. Yes, when the charge is by itself, they're straight. Once the charges with other charges, the lines start to bend. So this, oh, there's more in the chat. I'm sorry, I think there's more in the chat. Wait, I'm gonna wait, hold on. I think there's more in the chat. Let me just go, but it might be old. I've got the two devices going, so it confuses me. Hang on one second. Oh, maybe there's not more in the chat. Okay, that was old chat on my other device, I guess. But do please stop me if I'm missing somebody, because I love these questions. Hold on. So okay. So we're going to get to rules about bending the lines soon. Like there are rules about the lines bending and curving, just like, and by the way, if I did answer that person's question, I love to know that. But all right, so here's now rule number 4. At a point on the page. So remember, okay, well, I'll read the rule out loud, but then I'll try to explain it. What it says is rule number 4, at a point on the page, direction of field is represented by the tangent to the field line at that point. It's a little confusing, but that's what it says. I will explain it. But it says at a point on the page, direction of field is represented by tangent to field line at that point. Then it says under the break, it says magnitude of field in space is represented by density of lines per unit area on the page. Okay, this is a mouthful. Let me explain. Let me back up. First of all, remember the whole purpose of the field line diagram is to represent magnitude and direction of field of force per charge at every point in space due to some collection of source charge. Like you have a bunch of charge over here, it is affecting all of space. That's our whole belief here. If you've got a bunch of charge over here, it affects space everywhere over there. Specifically, it creates forces waiting to be exerted on test charges that might be located at any of those points in space. So the field line is supposed to be a picture that shows us what the magnitude and the direction is at every point in space of the force waiting to be exerted on every test charge that we could find in space. So we're trying to convey magnitude and direction. Now, remember again, the simplest way to convey magnitude and direction is a vector. If we were to look at any single point in space, we can still continue to imagine or believe that there's a vector sitting at that point in space whose orientation, whose tip-tail orientation indicates direction of field and whose length represents magnitude of field. We can continue to believe that. But the problem is we're trying to understand or visualize what the field is doing everywhere in a huge region of space. So we believe we can, in our brain, we can picture a field as a whole forest of vectors everywhere, but that becomes really, really cumbersome to draw. So what we have now, what we're discussing now is this smoother, simpler way of gathering up all those vectors and putting them together in one simpler picture, a picture of lines rather than vectors, right? Okay, so now we have these field lines rather than vectors. The field lines are there to indicate, to measure, to compute magnitude and direction of field. Okay, well, magnitude and direction. But hopefully you copy this. Tell me if you need to go back to this, because I'm going to go back to the pictures again now. I want to show you what I mean by magnitude and direction now. Do I want to continue? Yes, I do. Okay. If you go, is this a picture? Yeah. If you go to the, if you go to the B picture, can I do this? Does this work? No, hold on. Yes. Okay. Like say I pick this point right here, right here. That's just a random location. Can you see where my black arrow is, like where I'm hovering, right? You see that? Okay. If I pick that point right there, my question is, okay, what's the field doing right there? In other words, again, if I were a +1 coulomb of test charge if I found myself, if I were a little proton and I were sitting right there at that point in space, what would happen to me? How hard would I be pushed or pulled, and in what direction, right? Like that's the question that field is meant to answer. So as far as direction, I look at that point right there and I imagine a tangent line. I imagine a line tangent to the curve right at that point that I'm looking at. I imagine a line tangent to the curve, and the slope of that line, or the direction of that line, is the direction I would be pushed if I were a test charge. That's the direction I would be pushed due to this situation, this distribution of source charge, right? So first of all, I'm saying the direction of the field is given by the slope of the line tangent to the field line at a given point. Now, if you're saying, wait, tangent lines, like what? Like, why did come on, Yavra. Maybe you're saying, wait, duh, there's an arrow right there. Like, what? Why are you talking about? Like, I can see the direction. There's an arrow ahead. Yavra, why are you making this so complicated? Yeah, okay, the direction of the field is like the direction of the line. Isn't that all you're saying, Yavra? In a way, yes. If you understand what I'm saying, I am basically saying the direction of the field is the direction given by the field line. Yes, that is what I'm saying. But I have to bring up tangent lines because the point is, as a person noticed in the chat, these field lines are often curved. And curve means you're changing your slope continuously. You're changing your direction continuously, right? So to be precise, if we want to say the direction that you'd be pushed at any given place is the direction of the field line that you're near, just to be clear, we have to say, well, the direction of the field line right at that point. And since the direction of the field line is changing all the time, how do we understand or measure direction at a point on a curve? We use the tangent line, or what as the derivative, right? I mean, so it's tangent line just to acknowledge the fact that these lines are curved at any given. So the field lines are not highways. The field lines are not the way that a test charge would travel. That's part of what I'm trying to say is do not believe or do not misunderstand and think, okay, if I were a test charge, I would travel along the field line from the positive to the negative. That's not what it is. It's that the field line is showing at any point instantaneously what way you'd be shoved, what way you'd accelerate. And so you'd accelerate, if you were a test charge, along the line tangent to the curve at that point. And if you're following what I'm saying, you'd realize that necessarily, almost always, that would mean you'd fall off the line onto a new field line. And then the new field line would push you in a certain direction. Okay, so any given point in space and time, we get pushed in a direction that is indicated by the tangent to the field line at that point. Okay, and again, maybe, hopefully you get what I'm saying. If you hate the word tangent and it makes you shut down, then just recognize I'm just saying the direction of field is indicated by the direction of the field line. So that's direction. Now we have to talk about magnitude. Now we're going to get interrupted for a second, or possibly someone. I'm just stalling. Well, okay, I'm going to start. Hold on a second.
Victory Royale.
Nice. Okay, have a great time. Victory Royale. Awesome. Yes.
Everyone tell them that I got a Victory Royale.
I will tell them he got a victory. I can't admit that you play Fortnite. Oh, well, he plays Fortnite. Okay. But at least the Star Wars stuff got reissued and the lightsabers and all that. So we're all excited. Okay. Yes, you got a Victory Royale. Congratulations. Have a great time. Okay. Wow. Yes, I am that parent. Oh, so embarrassed. I like Pokemon so much better than Fortnite. Okay. Okay, so that's direction. That's direction. Now, wait, can I just pause for a second? Partly because I think this is getting abstract, and also because we just got to. Can I just get a thumbs up if you're still with me? I mean, an electronic thumbs up if you're still. Are you still hearing me? We're following this. Okay. Thank you, Caroline. Thank you, Amanda. Thank you. And I'm in a weird screen, so I can't see all of you. But thank you, Kevin. Thank you, Stephen. Okay. Awesome. Awesome. Okay. Thank you, Erica. Thank you. Okay. Okay. Now we're talking about direction. We did indicate, excuse me, now we talk about magnitude. Now we indicated this last class, but I want to say it again rigorously. Again, these are not vectors anymore. They're built from vectors. They allow us to picture vectors. Like for any given point in space, that I investigate in this field line picture, I could now imagine a vector being there, right? But the vectors are no longer there in the picture. So if you want to infer from the picture how strong the field is, if you want to infer what the magnitude of field is at a location, you cannot use length of arrow anymore. Length of arrow doesn't mean anything. That is my big point. So we have to use some other aspect of the drawing of the diagram. I'm going to pause now. I'm going to throw this question to you guys, just like I did in the other section this morning. I want to just make sure we're together. It's not a trick question, and there's no shame in getting it wrong. But I want to ask, how do we read magnitude from a field line diagram? And I am asking you, I'm asking for answers in the chat. I'm going to wait until I get 3 answers in the chat, whether it's accurate answers or not. I'm going to repeat the question. What aspect of the field line diagram indicates magnitude of field? So like, how can you, and I'm not asking for numbers, I'm asking for words, but I'm asking, if you look at this picture, say B, I think if you look at picture B, there's certain areas in picture B where you can tell that, or you're supposed to be able to tell that the field is weaker. In certain regions of picture B, the field is weaker. In other regions, the field is stronger. How do I know that? Like, how can you tell? What is it about? Oh, someone's in the chat. I'm going to look in one second. I've got the weird screen. Thank you. That's one person in the chat. I don't know what they're saying, but I'm psyched they're there. I'll see 1 minute, but that's one. I'm going to repeat the question again to get a couple other people in the chat. But the question again is, how can you tell from a field line picture how strong the field is? And not numerically, just comparatively, right? Like, how can you tell from the picture that some areas have stronger fields than others in that picture? Okay, there's 3 things in the chat. Awesome. I'm so psyched. I'm going to look. I can't wait. I'm so excited. There's 4 things in the chat. Oh my God. This is like, I'm going to a Pokemon gym. I'm going to meet the I'm going to meet the, okay. Oh, and they're all private. That's fine. That's good. Okay. Yes. Okay. Chat number 1. Oh my God. Oh yes. Oh wait, this is so exciting. I'm going to read. Cool, cool, cool. There's a lot of answers here. Yes, 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 yes. Awesome. Okay. First of all, thank you all. You're totally paying attention. Every single one of you that put something in the chat did answer the question. I'm not saying all the answers were 100% correct. And again, if it turns out that you put in a wrong answer, please submit for more points. You might be noticing that even though I'm still behind on some of your exams, a lot of all those game points are starting to come back again in big bundles. They will all come out in the wash. You will get all those points. And frankly, those are a lot easier, as you can imagine, to compute than the exams. So please don't give up on that. If you put in an answer just now, especially if you're nervous about your grade, submit it for participation. And if you find out in a minute that your answer is wrong, do not be ashamed. Submit it in the wrong answer portal. Like, by far and away, my favorite portal. So I'm going to say now, there's a lot of answers in the chat. Oh, and I was going to say all the answers in the chat are answers to my question. Even the ones that are like not perfectly right, they all show that you're understanding the question, which is great. Oh, cool. And someone just corrected him or herself. And I didn't even say anything. Wow. I have to say, I should open a portal for this next semester. Someone just literally like rethought it and put in a correction to his or her own answer. And I totally want to acknowledge that the second answer, the correction, is 100% correct. So good for you for self-awareness and like tracking this. So I'm going to say now, I'm psyched. And not that this is a competition at all, but you guys totally nailed this much more than the class this morning. Just saying. Okay. Oh my God, I can't believe I just said, okay. But so here's the deal. Well, okay, I'm just going to read out. Am I going to read out the answers? I'll read out the answer. I'm not reading names. No, I'm not going to read out the answers. I think it might embarrass some people. But here, the correct answer is the density of the lines, the closeness of the lines, the number of lines per unit area. You could express it a number of different ways. You're going to see in the notes, I express it with the word density. But any of you who's noticing that when the lines are more crowded together, when there are more lines packed per space, that is how we tell that the magnitude of field is strong. That is absolutely right. And yes, we said this Monday, it's not supposed to be a trick question, but yes, that's super important. So this is a different way of looking at things now, but we want to get used to that. When you look at a field line picture, you can tell that the field is strong, Luke, between the two charges, and it's very weak, like up here and down there. Okay, so I'm going to switch screens again. So that's a rule. Okay, and that's the rule we just wrote. Number 4, I didn't write it very well, but bottom line, direction of field is indicated by tangent to the field line, and magnitude is indicated by the density of lines per unit area on the page. Like, so to be rigorous about it, we're saying the number of lines per like square centimeter on the page indicates the strength of the field at the point in space being represented by that centimeter. And now remember again, this isn't just a rough thing. Remember that all these rules began with a scaling factor. So the whole idea, I'm probably going to go back to the pictures again in a second. The whole idea now is if you see twice as many lines over here as over here, we're literally saying field is twice as strong here. And actually, if you know your scaling factor strictly, you can literally calculate the strength of the field here and the twice as much as that over here, whatever. Like this is once you pick that scaling factor and you start following these rules and drawing according to the rules, then the field line picture really is telling us something numerical and something we can use for calculations. Okay, so that's rule number 4. Now we go to rule number 5. Now this goes, here's rule number 5, goes to one of the direct chat questions a few minutes ago. Note, as that person noted, field lines can and do bend or curve. They're not, again, they're not vectors. They're built from vectors, but they're not vectors. They can bend and curve, and they often have to. But they always bend, but always do so continuously. That is smoothly. That is, they don't make sharp corners. They don't make corners. They bend smoothly and progressively. And not only do they bend, they do bend, but what they don't ever do is cross. They never cross because each field line is a representation of field, and field is net electrostatic force per charge. Remember last week when we did that whole long computational problem where we figured out the field vector over here at the origin due to the point source over here and the point source over here, like the positive that was at like 5,4 and the negative that was at like 10,3 or whatever. Our whole belief there was this guy over the positive contributes a field vector to the origin, and this guy over here contributes a field vector to the origin, and then those two vectors get added together according to our long computation that we did, and the result is one final vector that points from the origin and indicates the field acting at the origin. So what I'm saying is that field, by definition, is the net effect. It is the final result of everything that's been happening due to all the charges that might be in a space creating field. So when we draw field lines, we are drawing that net effect of all the contributions already added together. So if ever you were sitting down to draw a field line picture, and then you were like, okay, there's going to be a field line due to that guy. And there's going to be a field line due to that guy over there. And so, okay, here they cross. That just means you're not done drawing yet. Now you've got to take those two vectors that you just thought of, and you got to add them together and get a final vector, and you'll get one line. So if you were to ever see a field line picture where lines were crossing, that means it's a rough draft. It means the field line picture is not complete. The field lines necessarily represent net effect. So they can't cross. Okay, they can't cross, but they can bend. They can bend. This now goes back to that person's question, like, why do they bend? Why do they bend? Okay, I'm going to switch the screens again. This is almost fun for me. Right. So look at this picture B, for example. Like this picture, which looks, again, it's like very intricate, right? But once you start it, when I first saw pictures like this, I was like, well, that's cool. But I mean, maybe if I'm lucky, I can understand it, but don't ever ask me to make one of those. It looks very intimidating. But when you break it down into these steps, you see the way that someone drew this, or the way a computer drew it, is they started with the positive. Well, they started with the scaling factor. They said, okay, in fact, I'm going to pause for 1 second. Yeah, sorry. They started with a scaling factor and they said, okay, I got a positive charge over here. I got an equal but opposite charge over here. So I'm going to start making lines. I'm going to take 16 lines or whatever, have them come out of the positive. I'm going to start drawing them as symmetrically as I can out of the positive, and I'm going to make 16 lines that as symmetrically as I can come into the negative. But it's 16 and 16. They all should be joined up. So we followed the next rule and said, okay, like all the lines that start at the positive should end at the negative. So for a line to come out of the positive and end at the negative, it had to bend, is basically what I'm saying. The bend is coming from the fact that there's no other way for, or the bend is coming from the fact that it is the simplest possible way to take a line that started at the positive and end at the negative. Is there something else I want to say about that? Yeah, I mean, so in other words, the way you follow these rules is you always, well, I'll say this again at the end, but you always do the simplest, smoothest, most symmetric thing you can to keep on following the rules. So the first rule was a scaling factor. The next rule was start at positive, end at negative. And that's the priority. Like anything that starts at a positive, if you can, end it at a negative. If you can't, go off to infinity. But the priority is it. Because put another way, why am I saying this? But put another way, you would never have a line that just started at infinity and went off to infinity. There'd be no reason for that line, right? So every line has a reason. It either being caused by a positive or it's being caused by a negative. So the whole idea is that first we make sure that all positives and negatives are being accounted for. I'm over talking this. You get what I'm saying? The lines bend so to make sure that any line that started at positive that could get to a negative does get to a negative. It bends to do that. But you see, they bend in the bend is progressive. Like there's very little bend in the short lines between the two. But there's more and more bend as we get to the lines that are pointing up. Everything is smooth and progressive and continuous. Okay. So lines can bend, but they cannot cross. That's the bottom line behind that. How are we doing on time? Okay. So that was rule 5. We're almost done. Here comes rule 6. Rule 6. A field line diagram should grow increasingly simple. That is increasingly symmetric and uniform as we look farther and farther from the source charge. That is, as you look farther and farther to the edges of the page on which a field line diagram is rendered, as you go farther and farther to the edge of the page, the lines should be looking more and more like parallel to one another. The pattern should be getting more and more simple. Why is this? Because remember, from any one charge, the farther and farther you go, the weaker and weaker the field is, right? Field line pictures start to get cut, and the field line picture from one charge is as simple as can be, just radial lines coming out in all directions. The pictures start getting more and more complicated. The pictures start getting more and more complicated as the collection, the arrangement, the distribution of source charges starts getting more and more complicated. Again, the field lines are just meant to indicate what information exists in the universe due to these source charges. So the more complicated the arrangement of source charge, the more complicated the field lines look. But they're only looking complicated because different source charges are doing different things, right? If this source charge is positive 1 coulomb and this one's like -3 coulomb, which we'll look at in a moment, then this is causing lines to come all out like that. This is causing lines to come in, but this one's like very dense lines. So they start curving and they start getting into very intricate patterns so that they can all join up and stuff like that. But the farther and farther away you go, the less field you're feeling from either one, the less field you're feeling from both. Therefore, the less conflict you're feeling from the field produced by both. Like the farther and farther away you get, you're barely feeling this guy's field. You're barely feeling this guy's field. So any difference between their two fields is making less and less of a difference. So as you get farther and farther away, what you should be experiencing is something more and more close to just like empty space, or just uniform constant field. And if you think about it, a constant field, a field of unchanging strength and direction, would be indicated by parallel lines, because again, remember, it's the density of the lines that indicates magnitude of field. Parallel lines don't get more or less dense as they go, like by definition of parallel. They're not getting closer or farther away. So parallel lines indicate uniform field. When you get to the edge of a piece of paper, the lines should look like the pattern should look as simple as possible as you get to the edge of a piece of paper or a computer screen on which a field line diagram is rendered. So that's rule number 6. We're almost done. Rule number 7 now, the last one. Hold on one second. I'm sorry. Okay. So the bottom line rule is you sit down to draw field lines, you attempt to follow the first 6 rules I just said, and frankly, even the 6th one will just automatically fall into place, but you attempt to follow the first 5 rules, and every time you ever make a choice to make your next line, what this rule says is you draw you make the simplest, smoothest, most symmetric choice you can that still allows you to obey the first 5 rules, and that will make the picture for you automatically. Like automatically, that's how the picture's done. So if you look at, so it says a field line diagram should be the simplest, smoothest, most symmetric picture you can draw once rules 1 through 6 are obeyed. And really it's 1 through 5 because 6 will automatically take care of itself if you really want to know the truth. I'm not even sure I should call 6 a rule, like it's an observation. But so here's what I mean by that. Yeah, like if you look, see, these are all different, right? Field line pictures, and they're right? They're intricate. They look very different from one another. And the one all the way to the right is the most intricate because what you have there is a positive source and a negative source, but of unequal charges, right? The positive has 3 times as much charge as the negative. So it has 3 times as many lines coming out from it as there are lines going into the negative. But as complicated as that, or as pretty, or as intricate as that picture looks, number C, the way it was drawn was literally just someone sat down, or a computer program sat down and said, okay, I'm going to start with this positive. I'm going to draw 16 lines coming out of the positive as symmetrically as I can. So they started drawing lines symmetrically as they can. or rather, to be honest, wait, sorry. Yeah. I'm sorry. Let me start again. Like they drew like 48 lines or whatever their scaling factor was. They drew like 48 lines coming out of the positive as symmetrically as they could. Then they went over to the negative and said, okay, the negative is only 1/3 as much charge. So it's only going to have like 16 lines coming into it. So they started drawing lines coming into the negative, only 16 of them. Again, where I get 16, I'm making up numbers, but I'm keeping them proportional. I'm saying that the positive charge is evidently 3 times as strong as the negative charge. So 3 times as many lines have to come out of it as go into the negative. So we start drawing lines as symmetrically as we can. But then we realize, okay, there's 16 going into the negative. Each one of those 16s must be hooked up with the positive. Because there's fewer negative line, like there's fewer negative, there's fewer lines coming into the negative than there are going out of the positive. So you first account for every one of those lines that's coming into the negative. You say every one of these that's coming in must have come out from the positive. So you start joining them up. So the lines start bending. Like you start, again, this goes to that private chat person question. You start with the most symmetric idea you can, but like the lines on the right, see the lines on the right side or the upper right and the lower right of the negative, they've got somehow to connect to the positive. So you bend them over as smoothly, as simply as you can, and you bend them less and less as you get closer to the positive, because you don't need to bend them as much. So all the negative lines are all bent so that they can all hit the positive, right? And the positives are also, and then you do the same thing. I mean, so now you've accounted for 1/3 of the lines. Now all the lines that are left from the positive, they have to just spread out and go to infinity, right? So, I mean, the ones of the positive that hook to the negative, they had to bend over and hook to the negative. All the rest just have to spread out to infinity, and as symmetrically as they can. So you spread them all out as smoothly and symmetrically as you can. And as long as every single negative landed on a positive and every single positive went off to infinity, and as long as you had no corners or no crosses or no line that suddenly did something wildly different from any line next to it, as long as everything is smooth and symmetric, there's no other way to make the picture other than this picture C. I'm not saying your picture would be perfect or mine would be perfect, but I'm saying this pattern that comes up in picture C, it's super intricate, yeah, and it's definitely different from the pattern in B or the pattern in A, but it's the one and only one pattern that you could come up with if you follow the rules that I just said, 1 through 7. Notice, lastly, I know we've got 8 minutes left. You see, like all of the pictures have some kind of all the diagrams have an interplay of symmetry and asymmetry. They're all about symmetry and asymmetry. They get more asymmetric as the distribution of source charge gets more asymmetric. In the limiting case, if you had nothing, you'd have perfectly symmetric field lines. You'd have just perfectly symmetric space. If you have a dot in space, you have field lines that are as symmetric as you could possibly imagine coming out from a dot. And the more you add dots, the more the field lines get more and more asymmetric. So field lines over here, the pattern of them indicates what's going on over here. The more different the field lines are over here, the more different the charges must be over here. Field lines are information. They are, so to speak, a difference that makes a difference. Okay, that's what we're going to say about that for now. I know we have 7 minutes. Okay, sorry. Now, I'm going to pretty quickly, in the 6 minutes we have, what do we do with all of this? Like, what's the point of these lines? All right. From these lines, I'm now going to introduce a concept called electrostatic flux. This is now a new concept. It's going to sound a little bit abstract at first, like all of this maybe does, but it's more concrete than it sounds. Okay, and I'm going to do this a little bit quickly. Electrostatic flux flux means flow in Latin. And there's many and there's many different kinds of fluxes that we measure in physics. There's electrostatic flux, there's magnetostatic flux, there's velocity, air pressure flux. But flux means flow, and in the specific case of electrostatics, electrostatic flux means number of field lines flowing through an area. In fact, I'm sorry, flux always ultimately in physics means some kind of stuff flowing through an area. More specifically, some kind of stuff flowing perpendicularly through an area. So in our case here, electrostatic flux means number of field lines penetrating through an area. Mathematically, we use capital phi to indicate flux, capital phi, that letter. We put a subscript E next to it to indicate that we mean electrostatic flux. And strictly speaking, by definition, capital E, electrostatic flux, is the double integral of electrostatic field vector dotted with infinitesimal area vector. Bear with me for a second. We've got 4 minutes. Don't be intimidated, please. I'm going to go backwards here for a second. What I'm saying is, in general, flux, in the simplest case, in the simplest understanding, electrostatic flux is E field lines through an area. Even more specifically, it's field lines times area. If there's no other takeaway, if suddenly you've got to go to Prism right now or something like that, if there were no other takeaway, flux is E field times area. Okay. We talk about it as an integral. Remember, an integral is a continuous sum. So what the integral is telling us is if you have some big area, you take a step, an infinitesimal step, you look at a little infinitesimal tile of that area, you ask how many E field lines are coming through the tile perpendicular to the tile, you multiply together. You multiply the size of the tile, like in square centimeters, by the number of field lines coming through it, perpendicularly through it. You multiply those two together, you get a number, and you throw that in your bag. Then you step to the next tile, ask how many field lines are coming through the tile, multiply the two numbers together, the number of field lines, and the per the area times the area of the tile. You throw that in your bag. Then you take another step, do the same thing, throw it in your bag. You add up all of these products and you get one big product of E field strength times area. And that big product is your answer. It's a continuous sum. Flux is the product of field times area. Now, why do we have to throw an integral in there? And why does it look like a double integral? Well, first of all, it's an integral because it's asking us to picture that procedure of adding up all the little sections to get one big area. And the reason we have to picture that procedure is just in case the amount of field strength is varying from bit of area to bit of area. This is why we always bring up integrals. If the field strength is constant throughout the whole area, then the E would come out of this integral and we don't need the integral, right? I mean, then it just becomes E times total area. So in the simple cases where E is constant, flux is field times area. But strictly speaking, it's an integral so that we can take into account the idea that the field might be changing from place to place. Why is it a double integral? Because strictly speaking, we're integrating with respect to two dimensions of space, to area. So strictly speaking, we're really integrating along length, and then we're like counting up the number of field lines per each unit of length and then multiplying by the number of field lines per each unit width. So it's a two-dimensional thing. So strictly speaking, it's really an integral times an integral. It's called a double integral. Don't be intimidated by that. You're not going to have to like overly concern yourself with that. But strictly speaking, this is one big two-dimensional integral. Lastly, why is it a dot product? Because we're taking into account direction. We're only going to count up the number of field lines or we're only going to count up components of field lines that are perpendicular to each element of area. Any field line that's going parallel to an area does not count as flux. So we use the dot product and this sort of we use the dot product to make sure to take into account the orientation of the area and whether and how it's aligned with the orientation of the field lines. Lastly, just let me emphasize one last, and so that's a technicality. I mean, yeah, it's a technicality. I mean, the fact that we care about perpendicularity is not a technicality. How we do it is a technicality. But last thing, please understand, bottom line, flux is a product. It's not a quotient. This is not density. This is field strength times area. You make the area bigger, you make the flux bigger. You make the field strength bigger, you make the flux bigger. That's good enough for today. You've been very patient. I'll keep catching up. You keep catching up. Everybody loves it. Have a good day, everybody. Thank you for.
Bye, Professor. Thank you.
Thank you very much. And you're, oh, I'm gonna start. Are you good, Rashman?